All right, so this video is going to be about absolute value and sign changes. And I'm using the absolute value function to really open up the discussion about sign changes. Big topic for us this term. All right, so first corrections from the last video. I got a video called context. I misspoke at the beginning. I meant to say how many times is 2 going to 6 and not vice versa. And I think I showed the progression of 1 gallon of gas, 285. 2 gallons of gas get me 570. 3 gallons gets me, I think, 855. But I think I showed that up in the wrong direction. So watch out for that. I think I posted 4 lesson sets so far. I'll do another one over the weekend, get some more repetitive practice. And what I want to suggest to everyone taking the class, look at every problem. The first stage of learning is following. And you need it every day. You need just to let your brain look at a particular type of algorithm, its numerical behavior, graphical, numerical, all of that every day. And eventually it'll start to make some sense. We started with a linear function. I gave you a x minus h plus k as a form. I told you, I wish you hadn't, been brainwashed with mx plus b. I shouldn't say that, that's derogatory. But I think people come in with mx plus b and they think everything's mx plus b. And some halfway through a semester, some people are graphing exponential functions as a line, mx plus b. So I think it's important that you see we've got about 12 to 14 different calculations we're going to study, and each one is like opening a new drawer of graphical and numerical change. All right, so this day one, I don't think anybody came in with the ability to actually quickly and easily write the equation of a line without any work, without any thought process, really. Well, it's a thought process, but you can get it down so quickly that now I see people doing it in 10 seconds or less. Some of the folks in the class are getting in under 10 seconds, 5, 7, writing x minus 5 plus 7, and looking at the change in y and putting it in the correct location, 5 to 9, 4, and creating multiples of 4 in the parentheses makes for easy division by 4. We're starting to see that happen. Okay, because we started a conversation. We've done it for 4 or 5 days now. We keep talking about it. When you keep talking about something and you keep doing something, you know stuff that other people don't know. Okay, so it's very important to look at everything. And why? I'll give you another example of why. The mechanics of writing an exponential function are not hard. The mechanics are not hard, but you got to take the time to see where every number goes. And I'm going to tell you what that's going to morph into. So I've had 5th and 6th graders write these correctly. So y equals 3. How do you get to 7? That's your first differential of 4. Next time, our differential isn't 4. Our second differential is 3 to 12, which is 9. That becomes the base of our exponential function. I'm a little more than doubling. Right? So I'm taking 4 and I'm multiplying it by 9 fourths, by 9 fourths, by 9 fourths, by 9 fourths, by 9 fourths. And when you double something, let's just double something. It's easier than multiplying by 9 fourths. I start with 1, it goes to 2, it goes to 4, it goes to 8, 16, 32, 64, 128, 256. Well, I'll stop there. All right, 512, I think. But bottom line is, you're starting with doubling a little bit, get you, twice as much. But when you start doubling a big amount, you get a big change graphically. Hence, exponential growth. And of course, we were tacking on 3 here. All right, so what have we learned so far? Well, we're trying to learn that b to the 0 is 1. We looked at y, and b to the 1 is b. And because I know that, I can easily write this as minus 1900 over 125. And so let's say I don't say anything else, and all you see is the number 125. Well, look at the graph and figure out where the heck it came from. Combine the numbers. Do everything you can think of with these numbers. Where did I get 125? Pause the video. Do it. I'll keep talking. 1900 to 2025. So the elapsed time from one data point to the next, I am looking at 125 years. So I'm converting years into amount. Subtraction of units and division of units. Getting rid of that. All right, now why is it important that you keep pace here? because this is going to bring us into studying e to the x, which is a member of the exponential family, where e is approximately 2.71. Extremely important base of an exponential function. Money in banking generally works in e to the x, and a lot of physics inquiries change every single one of these into e to the x. So how would I change this into e to the x? Well, let's make this a 0, because that gets complicated. But let's say a 0 gets you 7, and a 1 gets us 12. Okay, so that becomes x minus 0, which I don't have to write, and I'm dividing by 1. So this then becomes 3 plus 4. Let me do this one out. Approximately. I'm approximating now to get a feel for this function. I got to do it in my head. 1.4, 0.8x. Roughly. Okay. That function, 9/4, remember, is 2.25. Does it look like if I raise that to 0.8, I might get the number 9/4, which is 2.25. So I'm sorry, if I raise 2.71, will I get to the 0.8? What did I just say? 2.25. I'll go decimal. Well, I know what 2.71 to the 1 is. It's 2.71. That's a smaller exponent. So I hope intuitively you can say, you know, that helps us. Now, exponential functions will diverge, but if you put that function, it pretty much overlaps it. I mean, eventually a small change in x is going to be a huge change in y. So more and more error as I move to the right. But by and large, I've got a feel for one of the numbers. So how do we sketch this? How do we sketch 3 plus 4 e to the x? Well, I'm going to show you with practice, rapid fire five practice problems, and we'll standardize how you practice that. And many of the students coming out of classes, Algebra 1, Algebra 2, or Pre-Cal, can graph that in 10 seconds or less. I want you to get there. But if you don't stake and work at the pace we're setting right now, if you're not looking at everything and not considering this, then this whole section is going to get tough. So most of the students coming out of those classes, or at least half, could have done that as quickly as I did, find the exponent. So let's get rid of this. And where does this take us? Eventually, learning how to do that allows us to see the rules of logarithms. Allows us to see them. And I hope that happens for you in this class. Right? But it starts here. Right? Where else does this take us? It takes us to inverse. All right? The inverse of this is x equals 3. And it passes through the points 7, 0. And it passes through the point 12, 1. All right. So let's take a look at this. Let's graph 0, just the mechanics. 1 log x minus 3. Throw a, how far is 3 from 7? 4 units. And how far is it from 3 to 12? 9 units. So when I put 12 in, I get 9/4. And what do you put on top of a 9/4 to get 9/4? 1 plus 0 gets me that point. When I put in 7, 7 minus 3 is 4. What's 4 divided by 4? 1. What do you put on top of 9/4 to get a 1? A 0. What's 0 times 1? 0 plus 0, 0. In other words, everything we're doing here bleeds into something else. All right. So that's process. That's what I meant by this is about, well, I guess I didn't say process at the beginning, but I will when I upload it. This is a little lecture on process, absolute value, and sign changes. And now we're at the gateway problem, absolute value. Okay, so let's start with y equals x. Y equals x means whatever x distance you travel, the y is the same. So it looks something like that. Okay, so if I went over 2, then I'm going up 2, so on and so forth, 0, 0. Let's slap in, well, what is absolute value? Absolute value measures change from 0. So if I go over 5 units, I've walked 5 steps. Well, what if I went back 3 units? Then I've walked 3 steps. Okay, so it takes that negative number and turns it into a positive. Distance is always positive. So when I slap an absolute value on this, values are y values, and all these y values are negative. Okay, well, they become positive. And I get myself a V-shaped graph. A V-shaped graph for absolute value with 2 linear components, a line on the left and a line on the right. Line on the left and a line on the right. Okay, so let's graph something else. Let's graph y equals x minus 3. Well, the most important number here is 3, not the y-intercept. The x-intercept. That's what's really important. I'm measuring change. When I put a bracket around this, this is linear change from 3. So if I went over to 5, how much have I changed by? 2 units. If I went back to 1 minus 3, I've gone down 2 units. Okay, so just graphing the function x minus 3. I know you were taught go down 3, up 1 over 1. Okay, I get that. There's our line. Algebra 1. Absolute value. What happens? The y values, these are all y values, become what? Those are negative. They became positive right here. And if I want to know the y-intercept, put in a 0, and I can see I'm at 3 as well. So that negative 3 down here became positive. All right, good to know. All right, let's look at another one. Let's look at y equals, 2x minus 10. All right, what's 2x minus 10? What's the critical number? It's not negative 10, it's 5. Why 5? Because I'm going up at 2 to 1, and that's where the sign change happens. 2 times 5 is 10, minus 10 is 0. 2 times 6, 12 minus 10 is 2. 2 times 4 minus 10 is negative 2. So what happens when I slap an absolute value on that? The negatives become positive, and I get a V-shaped graph. Okay. So let's just talk about sign changes in general. X minus 2. Sign change at 2. But what happens if I square it? I don't think these negatives come out of the problem anymore. And I don't think I get a linear function anymore. I think I get a quadratic with a vertex at 2, 0. With no sign change. What if I made it a 3? Well, now I got a cubic. I think I got a sign change. At 2. I think I will from negative to positive. Okay. All right, so I said what I wanted to say there. Now, let's look at absolute value with x minus 2 times x minus 4. Okay, we're trying to learn how to, we haven't spent enough time on that because I know it's a gap from algebra 1. So what I'm hoping you see is an x-axis here, critical numbers of 2 and 4. And I hope you can see it's an x squared graph, cup shape up. That's what it looks like. Well, that's got negative values. What happens if I slap an absolute value on it? What's it going to look like? You keep pausing the video. I hope you see that these negatives become positives. Don't have any sign changes now. I've got positives, a 0, positives, a 0, positives. That function's never negative. Well, it couldn't be negative. I got an absolute value around it. All right. So let's go and let's do 3 things with these absolute value problems. And then I'm going to talk more about sign changes from the context of other functions besides the absolute value. And this course, basically the course I'm designing is every problem I've seen students have coming into calculus, foundational problems, I'm trying to put in a worksheet and correct. So that if you get to that level of math, you have a chance at thinking about the calculus concepts and not the mechanics that you need in order to think about. All right, I'm hoping we can get that done here. All right, I'm hoping we can get to a little calc by the end of this semester. All right, so step one, pause the video. You try each of these things. I'm not going to pause. Sketch f of x. Okay, what can I see? V-shaped graph. Sign change at 4. X minus 4 changes signs at 4. You put a 3 in, you get a negative. You put a 5 in, you get a positive. So I am getting rid of that sign change, but that's my vertex. I know 0 is to the left of 4. So I'm going to put a 0 here. And I'm going to plug 0 in. And if I do, I get 17. Okay, which means that over here, 8 also gets me 17. That's the same height. We're going to write this as a piecewise function. I haven't talked about pieces yet, but I see a linear function on the left that is decreasing because you follow graphs from left to right, and a linear function on the right that's increasing. And so we draw Alfred Hitchcock. Didn't do a good job. And on the left side, I have the line. It's actually minus 3 times x minus 4 plus 5. But that's only true until I get to an x value of 4. So I'm looking at x values less than 4. Let's put 0 in and see if this gets us 17. 0 minus 4, negative 4 times negative 3. 12 plus 5, it sure did. This one's going over from 5 to 17 is up 12. From 4 to 8 is a change of 4. That's positive. Over here, 17 to 5 is down 12. And 0 to 4 is up 4. That's a slope of negative 3. This is a slope of positive 3. So all I have to do is write x minus 4 plus 5 for x is greater than or equal to 4. We're going to do it every day. We're going to be on it's going to be on every test for the rest of the year. No gaps allowed. So now I want you to find f of x. Yeah, you can see that. F of x equals 26. Well, sometimes I just don't want to have to think. So I'm going to use the pieces to do that. Okay, I know it's, and 26 is where? 26 is above 17. Right? It's almost the same distance. So height of 26 is here. And I want to find that x, and I want to find that x. Okay? And I'm going to use the pieces. And then I'll show you what I would do with this problem. Do the problem again, because I don't write all this stuff up. I just put the answer on a piece of paper, and I'll show you how you can do that. All right, but what I am going to do is I am going to solve this for, what did I say? A height of 26. All right, so let's set this to 26. And when I do, I'm going to get this first x answer. I'm going to get x1. Okay, and I know that the number 4 sits equidistant to x2. Okay, but I'll do them both out. So let's see, where's the best place to do this? Minus 3x minus 4 plus 5 equals 26. So I'm going to subtract 5, 21. I'm going to divide by negative 3, and I'm going to add 4. So negative 3 gets me 26. How far is it from 17 to 26? 9 units. And what's 3 times 3? The slope, 9. I've changed by 9. So I already know the answer to the next one. If this is negative 3 and that's 4, I'm changing by 7. This one should be 11, but let's find it by using this function equaling 26. So I'm changing that. First step is the same. I'm going to get a sign change. I'm going to add 4, and there it is. It's 11. Okay, well, I'll let you find more shortcuts, but I didn't have to think. And so now I have this sign chart where my y values here are bigger than 26, and my y values here are less than 26. I can already answer this question. When is the function bigger than 26? When x is less than, oh God, I don't usually use these symbols anymore. When x is less than, what did I say? Minus 3, or when x is greater than positive 11. There, I finally got it out. It's much easier to do interval notation. Negative infinity to -3, union also 11 to infinity. And that matches up with that picture that you probably learned in grade school. Now, what happened if I wanted f of x less than or equal? Well, equal means that I close that dot, and I make the parentheses a bracket. And that shows that those numbers, 11 and -3, satisfy the equation. Repetition's our friend. Let's do it again. You're pausing the video. You're trying to do it. Okay, I need to see this. Yes, so I can erase this stuff. Get it out of the picture. So it doesn't get in our way of our considerations. All right, so you're looking at that, pausing the video. And what do I see? I see that this A term is less than 0, so it's a V shape down. I can see what makes 0 here. -4 is where the sign changes will occur. Or -4 centers. I'm not quite sure what I say what I said there. -4 gets us 12. I can see that. Put a -4 in, crunch the numbers. You'll get 12. And I know that -3 should get me 10 because I have a 2-to-1 ratio of change. Okay, but we don't care about that, but I just thought I'd say it anyway. And I want to write this as a piecewise function. All right, so Alfred Hitchcock, having trouble with his nose today. Okay, so y equals, this is another way of writing this function. I'm going up on the left, so my slope is positive 2x plus 4 plus 12 until I get to 4. All right, because then I switch to going down, which is -2x plus 4 plus 12. X is less than or equal, greater than or equal to 4, excuse me. All right, so then I can look at that and maybe do it in my head. All right, I know 4 is, I don't want it to be confused on the number line, but 4 centers this. Remember that 4 centers. So I'll just do this one. When does this thing equal 4? Well, I got to subtract 12. That becomes -8. I can divide by 2, -4. -4 plus 4, I think 0. So on the left side of 4 is a 0, which means to the right side of 4 is an 8. Those should be the numbers that I can get pretty easily. And if I'm going down, then I know my answers are bigger than a height of 4. So here's a height of 4. Right? The numbers are between 0 and 8. But I've been up for a long time, been doing quite a few math problems, and my brain at the end of these videos gets tired. So let's actually do it out. 2x plus 4 plus 12. Let's set that equal to, I guess I said 4. So there's your -8, there's your -4, add 4, there's your zeros. Yes, so those two numbers were correct, 0 and 8, because 4 is the symmetric point. And you can just trial and error, put a number bigger than 8 in, put a million in. Put a million in here. So the absolute value of a million is a million times -2 minus 2 million plus 12. Minus 2 million plus 12. Is that bigger than 4? Minus 2 million? I don't think so. So you get false, true, false. So what would the interval notation be? I am bigger than 4 from 0 to 8. I wouldn't use interval notation. I would say x is greater than 0, less than 8 in that instance. Okay, I hope I talked about that enough a little bit. We'll do one more. And then we got a couple of sign changes with different functions. All right, so, boy, I must like the number 4 today. Right, because if I plug in a 4, what do I get? I get the absolute value of 0, so this thing hinges at 4, and I get a 7. And if I said that you're a babysitter, you're 10 years old, you're babysitting your little brother, and the parents say, hey, I'll give you $3 an hour, right? And then when you turn 11, you do a good job, I'll double your wage. You're going to know something about the rate at which you're earning money. All right, so this is cup shape up. So let me graph it over here. Yep, cup shape up. 4 gets me 7. My y-intercept is to the left of 4. So I plug a 0 in and I get 12, 24, 31. Okay, now you can really do, I can see that my multiplier is 6 here, right? I'm making $6 an hour once I turn 11. All right, so you could theoretically write these as 31 to 7 is down 24 and a change of 4 units. I hope you can see you're going down at 6 to 1. So you could have done that, saved yourself some computation, and then put for the critical number, x minus 4, this point, right, 4, 7. You could have done that, and that occurs for x's, boy, getting a tired brain if I don't botch this up, so I have to do it again. And then you're going up on this side at 6, x minus 4 plus 7, comma, x greater than or equal to 4. Could have done that. All right, yeah, I am getting tired. What do I want to say now? I don't want to get too complicated because I'll butcher something at the end here and have to do it again. So where does it equal 21? All right, well, because I got the eraser and I'm getting tired, let's get rid of that. Let's just solve each equation for 21. And as you get better, you take your shortcuts. All right, I know whatever answer I get here, however far it is from 4, I got to go backwards, forwards 4 for this one. Backwards, forwards. All right, so let's just do this in our head real quick. Equals 21, I'll do it here. Take away 7, 14, divide by, oh, am I going to get some fractional answers here? 14, yeah, I am. So let's change this to 23. Let's make it 23. Make our life easier. So 23. All right, take 7 away from 23. I still didn't get a multiple of 6. All right, I'm learning on the job here. All right, so I want a multiple of 6. So 21, 30 is a multiple of 6. So let's go 37. Let's go to 37. That's how I make these problems. All right, so I want to know when it equals 37 and when it's greater than 37. Yeah, I can tell I'm starting to fade. All right, so let's do this one, 37. Let's take away 7, 30. Let's divide by -6, -5, and let's add 4, -1. How far is -1 from 4? -1 from 4 is 5 units, so my next answer should be 9. We can do it here. Take away 7, 30, sign change here, so we get 5 that time. 5 plus 4 is 9. All right, so we got our V-shaped graph. We're going to a height of 37, and we want to know when we're above 37. And I know that answer is 9, that answer is -1, and I'm going to erase the negative y values. And I have -infinity to -1, union 9 to infinity. All right, this goes to infinity. The x's go to -infinity. These y values are going to positive, and these x values are going to infinity as well. So I didn't need to mention that one. All right, at least I'm talking about it. Now let's go back to just sign changes with a different calculation. What's the critical number? 2. When is this thing greater than 0? Plug a number in. 3, 4, 5, 6, positives. Put a number less than 2, negative. So x is greater than 2 from a graphical sign chart perspective. What happens if I squared that? If I squared that number? Well, x minus 2 is this graph, right? Cuts through 0 at x equals 2. And when I square these numbers, I get positives. I don't get linear change, I get quadratic change. But when is it greater than 0? Pretty much always, except at 2. But their sign chart could do it. It's only one number. Put a number in bigger than 2. 3. Yes, true. Put a number less than 2. Still true. All right, so what happens when we get a polynomial like this multiplier here? Well, in calculus, the quickest way to get that, and really is important that you can sketch those, but you could, at this stage, just do a sign chart. What are the critical numbers? 0 is critical. 4 is critical. 8 is critical. Okay, and what am I going to get if I do that? Well, I'm actually going to get concave down, concave up. I'm going to get that graph. From a sign chart perspective, that's what I was going to do first. You just put numbers in and see if it's true or false. Put 1,000,000 in here. Million, million, million. I think you're going to get an answer bigger than 0. And I know what exponents these are to. So I'm going to get a sign change. False, true, false. So when is it bigger than 0? Interval 0 to 4, union 8 to infinity. All right. I said less than 0 is going to get a false. It's going to be a negative answer. Let's see if that's true. Let's put -5 in. -5 times -9 times -13. Is that greater than 0? Is a negative times a negative times a negative bigger than 0? The answer is no. We can also use this technique for many other situations. And you have to have that skill. You take a calculus course because you're going to study rates of change. And when rates are positive, grandma's heading north on 91. And when the first derivative is negative, her velocity is negative, she's heading south. So you're going to be analyzing physical contexts. All right, so when is x minus 4 over x plus 8 times x minus 2 squared? Now let's see. Do I want that one? Yeah, let's do it squared. When is this thing greater than 0? Sign chart. I'm not going to graph that. I can see critical numbers. 4 is critical. I can see -8 is critical. And I can see that 2 is critical. Why did I draw a dot there? Because I know when I square things just a minute ago, I didn't get a sign change. So we have 1, 2, 3, 4 intervals and 3 numbers to figure out if they work or not. And I can immediately tell you if they work or not based on whether I get this part right or wrong. And then we'll check, because I know I'm not going to get a sign chain here. If this is false, it's going to stay false. If this interval is true, it's going to stay true. Well, let's find out why. And this is the last one we'll do. All right, pick a number bigger than 4. 1,000,000. 1,000,000 minus 4, 1,000,000 plus 8, 1,000,000 minus 2 squared. By golly, I think that's true. I'm suggesting that we're going to get false, false, true. I'm suggesting that our answer here is negative infinity to -8. Let's make this or equal to. Let me make it or equal to. All right, does -8 work? -8 plus 8 is 0. Can I divide by 0? No. Union. Can I use 2? 2 minus 2 is 0. I can't divide by 0, so no. 2 doesn't work. Does 4 work? 4 minus 4 is 0. 0 divided by numbers is 0. So that's true. Now, let's prove that a number between 2 and 4, I would say 3, might be the easiest. 3 minus 4, -1. 3 plus 8, 11. 3 minus 2 squared, 1. So if I put a number between 2 and 4, I would say my first parentheses is negative. 2 plus 8, positive. 3 minus 2 squared, positive. All right, so I get a negative quantity. Is a negative quantity bigger than or equal to 0? I don't think so. False. Let's put 0 in here. We put 0 as a number between 2 and 8. I think I'm still going to get false. I don't think that is going to change. Right? Or I think if I put 3 in, 5 in, 3 in, I get a sign change. Right? So therefore, if I change a sign, it used to be positive when I put bigger than 4 in. When I put 3 in, I got 1 sign change. Didn't affect these. I could put 5 or 3 in here. 5 or 3. And when I add 8, I'm positive. I could put 5 or 3 in here, and when I square, I'm positive. But if I put 5 or 3 into this, I get a sign change. And in a division problem, when you get a sign change, your answers change from positive and negative or vice versa. Okay, so I hope I proved that. So let's put 0 in real quick again. 0 minus 4, negative number. 0 plus 8, positive. 0 minus 2 squared, positive. I still get a negative number. You can plug something in. less than -8 because I'm running out of breath here. Whew. Finally done. All right. So it's really important that you hear these lectures. You work on it in class. You take a test. You find out what you don't know and you figure out how to get it right. And the way I grade, I look for the highest test score because all the tests are very similar and you can't get something right in math until you learn how to do it. And if you get it right, as far as I'm concerned, you learned. I don't care how long it takes you. Right? Everybody learns at different paces. Some students are able to, get to a little calculus by midterm, and some students are still trying to fill in gaps from Algebra 1. Regardless, make some gains, practice, and think. All right. So I hope that I apologize for the length of time for these, but it's early in the term and we want to be able to get good at things. So we got to have stuff in front of us that we can practice a long time. That's my belief. Okay. Toodaloo.